Hi guys, so today I'm going to be talking a little bit about the first law of thermodynamics, and I'm going to try to explain it in a way that is just simpler and super easy to remember and use throughout your course. So there are a couple different ways that the first law of thermodynamics can be expressed. The easiest way, we'll say, is delta E equals to Q minus work. So the Q is the heat transfer, the W is work. And so heat transfer minus work is going to be equal to the change in energy. So in both the heat and work, we can use delta Q and delta work, which is going to be the change in heat and the change in work. So this is the simplest way of using the first law. Okay, so a more complete way of describing the first law of thermodynamics is as shown above. So the first part is still going to be the change in energy. Then we have Q dot, which is the change of internal energy, minus W dot, which is the change in work, plus, and we have two Riemann sums. So the first Riemann sum is the mass flow rate in the system, which we have three different components that are included. So we have m dot, the mass flow rate, then we have the three, we have the enthalpy, we have the kinetic energy, and we have the potential energy. Then we have the second Riemann sum, which is the mass flow rate out, and we have mass flow rate, and it's the same thing as in. So it's just the difference between the two. So altogether, that is the most complex form and most complete form. So in most of the problems seen in this course, many different factors in the formula can be eliminated or ignored. So most of the time, well, if you are in steady state, the portion of the formula that is the change in energy will be 0, since there is no change in energy because you're in a steady state. So another part of the formula that can be ignored is the kinetic energy part. If the velocity of the substance is very, very small, or if the value of the whole kinetic energy part is way smaller than the enthalpy, because the difference will make no difference. So another component that can be ignored is the potential energy component. It can be ignored if the height difference is super, super small, which most of the time it is, or if its value is way smaller than the enthalpy value, because then it won't make a difference, just as kinetic energy. Taking into account all of those terms that we can ignore and everything, here is a simplified version of the first law of thermodynamics that we will use in most of our problems. So now we're going to see a little sample where we have a heated flow system where we can use the first law. So if the water flows through a pipe with a heater and the mass flow rate is 1 kilograms, if the inlet temperature is 20 degrees Celsius and the outlet temperature is 80 degrees Celsius and heat is added to the fluid, what is the heat transfer rate? So in this case, let's write down the important information. So we have the mass flow rate, m dot, which is 1 kilograms per second. Then we have the inlet temperature, so T in is 20 degrees Celsius and T out is 80 degrees Celsius. We assume no shaft work because it is given. It says W dot is 0. So W dot equals to 0. And of course, we can ignore the kinetic energy and the potential energy. And they also give us the specific heat of water, which will be useful later on. So 4,180 joules per kilogram Kelvin. Perfect. So now we're going to set up our equation. So we have dE over dt is equal to q dot minus w dot plus m dot times h2 minus h1. So in this case, we can ignore this goes to 0, work goes to 0, so we have q dot equals, sorry, over here it's the other way around, it's 1 minus 2, perfect. So now we can switch it over, and because of the minus sign, now we can inverse h2 and h1. So we're going to have m dot h2 minus h1. Perfect. So now this is the setup that we have. So if we want to change, since we don't have the enthalpy, but we do have the temperature, if we want to change that, we have the temperature over here, but we don't have H. So if we want to get H, we can use H equal to CP T. So we can replace them in the formula over here. Q dot equals to M dot times CP T2 minus CP T1, which we can factor out. So we have M dot CP T2 minus T1. Once again, now we can plug in the values because we have the values over here. So we have 1 kilogram per second times 4,180 joules per kilogram Kelvin. And then we can work with the temperature, which we have 80 minus 20. Now, when we calculate that, that is going to give 250,800 watts, which means that Q dot is equal to, we're going to simplify it a little bit, 251 kilowatts. And just like that, using the first law of thermodynamics, we can find the change in heat in a heat exchanger.